Hey, Calc students, time for another FRQ on old AP exam. This is from 2019, question number 1. And since it's a question number 1, it is a calculator-based question. And this is of the format of two rates. So we have a rate of entering, a rate of exiting, or it's a rate of increase, a rate of decrease, and typically a initial condition. So let's read the question, get a feel for it, and then we'll go from there. So it says, fish enter a lake at a rate modeled by the function e, given by e of t is equal to 20 plus 15 sine of pi t over 6. Fish leave the lake at a rate modeled by function L, given by L of t is equal to 4 plus 2 raised to the 0.1 t squared. Both e of t and L of t are measured in fish per hour. T is measured in hours since midnight at t equals 0. So, basic concept here is we have some sort of probably a stream or river heading into a lake, and theoretically here the fish head into the lake for the day, apparently, and that's their E of t. They swim around part of the day, and some are leaving. Leaving the lake, maybe going downstream here, and this is the L of t equation. So we have fish entering and exiting the lake, and at t equals 0, there's no statement about an initial condition or how many fish are in the lake at time equals 0, and which is a little unusual. Oftentimes there is an initial value. That's basically all we're given. So we have a sinusoidal and an exponential type function. And they're probably going to be asking you questions about how many fish are in the lake, what's the rate of increase, something like that. So let's see what it says. So starting with part A. Part A says, how many fish enter the lake over a 5-hour period from midnight, being t equals 0 to 5 a.m., or time equals 5? Give your answers the nearest whole number. Well, this goes to the basic concept here of what do you get when you integrate a rate. I'll call that dt. Whenever you integrate a rate from a to b, the slang answer is whatever the rate is producing. Well, if we have the rate that fish are entering the lake and we integrate that rate, we'll get how many fish entered the lake. So how many fish entered the lake? You're looking for the function for how many fish entered the lake, and you're just going to integrate from 0 to 5. So all we're doing is integrating the rate they enter the lake, 0 to 5, and we take advantage of our calculator. Now this function here, we'll write this here a little bit bigger here. So this is 20 plus 15 sine of pi of t over 6. So we could integrate that with some u sub, and it would be kind of ugly, but it's a calculator question, so we're going to take advantage. So this is a calculator question, so we will just take advantage of our calculator, and let's put that in. So we're going to integrate from 0, oops, clear out of there. We're going to integrate from 0 to 5, and then we just have to carefully enter our function here. So we have 20 plus 15 sine, and our numerator is pi times t, our variable will be x, and we're divided by 6. And that is the rest of the angle statement. Just keep track of your exponent, or your parentheses on here so you don't have an error. And we integrate that, let the calculator do the work, and we get 153.458 rounded. Now the actual question says how many fish enter. It says give your answer to the nearest whole number, so just follow your rounding rules. And so since 4 is less than 5, we are going to round down, and we would say 153 fish. Done. Okay. Part B. Part B says, what is the average number of fish that leave the lake per hour over the 5-hour period from midnight to 5 a.m.? Well, what they did was they tried to trip you up just a little bit, but this question is really just about average value. And whenever you want average value of a function, average value of f, that's equal to 1 over b minus a times the integral of a to b of f of x dx. And so instead of using the word value, they use the word number. And so you just had to recognize that that was average value and put a 1 over 5 out front. And so 1 over 5 minus 0 would be 1/5. And then we're integrating from 0 to 5. And it says this is the average number of fish that leave. So we have to switch to the other function, which is the L function. And this should give us what we're looking for. Okay? So you don't want to confuse average value with average rate of change. They're not asking about an average rate of change. They're just saying the average number. And what's the average value of the function representing leaving? There's your setup. So we'll go back to our calculator. And we will say 1 divided by 5 out front. We'll put that 1/5. And we'll grab the integral again. And we'll go from 0 to 5. And now we just have to enter the exiting function, which is 4 plus 2 raised to the 0.1 x squared. And again, your calculator is going to be using x instead of t. And there is that integral. And we get 6.059. And this is going to be the average number, so it's going to be 6.059 fish per hour. Okay. Next question, C. All right, so you should be anticipating that when you have the two rates question, it's going to be something about the amount of fish, and we're going to have to build that total amount function. So that's going to come up here. It says, at what time t is the greatest number of fish in the lake? Justify your answer. Well, this is the question. Whenever you hear the word greatest, that's really just maximum. And so when's the maximum number of fish? Well, when you hear maximum or minimum, you should think, well, in order to figure that out, I'm going to need critical numbers. And how do you find critical numbers? By taking the derivative of the function, setting equal to 0 and undefined, and testing it. So if they want to say what's the greatest number of fish, I better figure out a function that represents how many fish are in the lake at any given time. So that's where we go to this idea of there's always three things involved. 1 plus 2 minus the third thing. And this template that we use frequently for these questions is how many fish are in there initially, and we add to it the integral of increase, and we subtract from it the integral of decrease. And these are the rates those are changing. So if we look at this particular question, we have a of t is equal to, our initial amount is actually 0, according to the question. And we're going to add to it, we're going to integrate from 0 to t, the function that represents the rate of the fish entering the lake. And so that's going to be the e function. And you always have to remember that if your unknown time, which is on your interval, you have to have a different variable for your integral. So you can change it to anything you want. I'm just going to switch to x. But it doesn't make mathematical sense to have the same variable here because they're both changing at different rates. You can't represent that the same. So there's my initial value plus my integral of the increasing amount, and I'm going to subtract the integral of our decreasing amount, and that was the L function. And I'm also going to change that variable to be x. So this is our function representing how many fish are in the lake at any one time. Now this is the function that we're going to have to take the derivative of and then get our critical numbers. Well, I'm just going to clean this up ever so slightly by just taking out the 0. And I would say if you want to know how many fish are in the lake at any given time, a of t is equal to the integral of 0 to t of e of x dx minus the integral of 0 to t of L of x dx. Now you may notice if you wanted you could put those in the same integral, but that's only because our time interval is the same. That's not always the case for questions, so I tend to leave them separate. So for the sake of space here, I'm going to move this over and make a little room here. And let's see if we can find some critical numbers and get to the bottom of this question here. So this is C continued. Okay. And let's go back and recopy this. So a of t was equal to the integral from 0 to t of e of x dx minus the integral of 0 to t of L of x dx. Okay, so there is our function. Well, we need to take the derivative of that. So I am going to take of this entire function here, I'm going to take d dt of this. I think we'll get this out of here so that doesn't look confusing there. So I'll put C and I'll just put continued. Okay, and so I'm going to be taking d dt of this. And this is where this little issue that comes up that can be confusing. And hopefully you're starting to see it enough times here where it's going to register and not be an issue. But if I take the derivative of a function a, this is just going to turn into a prime of t. But I'm taking the derivative of an integral. And so the derivative of an integral, they knock each other out because this is the derivative of an antiderivative. But I have to respect the interval values. So this is an issue that comes up in every calc textbook about the second fundamental theorem, which is always incomplete. So, for example, you'll see this in every calc book. So usually they'll say something like a to t of f of x dx. And what they will put for the answer is f of t, which is true. And that'll be in the heading of every second fundamental theorem book. But there's so much more going on here that you don't realize that when you do this. There's 4 things that happen, and it's very important you get this. So notice the variable of for my derivative operator is t, which is the same as my interval, not the same as my integral. So although this derivative knocks out this integral, I still have to do the fundamental theorem with my interval values. So I am going to replace x with t, because that's my interval value, times the derivative of t, which is 1, minus f of my second interval value, which is a, times the derivative of a. Well, a is a constant in this case. This is not a variable. And in fact, you could put a 0 there if you wanted, but the derivative of that constant is 0. Well, all of this simplifies down to give you f of, right here, by the way, sorry, I should have put t in here. Wrote x. This is f of t times the derivative of t, which is 1, minus f of a times the derivative of a, which is 0. And sure enough, you get f of t. And that's why this is written in every calc book. But you have to see here that there was 4 individual things that were going on here. And you have to remember that. Because this can burn you in the future if they decide to have interval values where this is a variable also. Or maybe this is not just t, it could be t squared or t cubed or 4t or something like that. So this is misleading about how simple it is. So just remember there's all those things going on. The reason that's important is up here, when I take the derivative of this integral, it does simplify really nicely, but I like to stress this. So really this first thing is going to be e of t times 1 minus e of 0 times 0. That's actually the derivative of this whole term. And then I'm going to subtract the next one, which is L of t. The derivative knocks out the integral, but I replace x with t, times 1 minus L of 0 times 0. That's really all that's going on. Now, when you simplify it, you just wind up getting e of t minus L of t. So a lot of students accidentally get the right answer the wrong way here. They didn't realize all this other stuff was going on, but they didn't get burned by it because 0 was a constant and the derivative of t was 1. But there really was a lot more going on here. So, at any rate, we have our derivative. And here it is. And we're going to say, all right, I need critical numbers. When does this equal, or when is this undefined, and when is this equal to 0? So now let's go ahead and look at our functions. Now, as it turned out, it's the sinusoidal minus the exponential, and there's no domain restrictions. This thing is never undefined. But now we have to say, all right, when is e of t minus L of t equal to 0? And this is a pure calculator question. If you want, you can graph this and look for x-intercepts, or you could say, well, what if I graph them independently and see where they intersect each other? Either method works completely fine. So in either way you do this, you're just going to graph these in your calculator and see. I'm going to do the second version here, and we'll see where they intersect. And by the way, important on this one, they give us a slightly different domain. They tweaked this a little bit for the time. On this one, they increased the time here. It was 0, less than or equal to t less than or equal to 8. Whereas the question before, down here, they were 5. And the first two questions, they were with 5, and this one they jumped up to 8. So we're going to put this in the calculator and see where they intersect. Okay? So let's see what we get here. So we're going to go to y equals here, clear that out. So the e function, which is 20 plus 15, sine, and my numerator there is second function pi, x, close that, divided by 6, close the angle. Okay? And should be good there. And then the second function is 4 plus 2, and the exponent of 2 is 0.1x squared. Okay? And then we'll just go zoom standard and we'll see what happens. Okay, now if you graph this, part in a normal year, calculator literacy is a really important skill, and they seldom give you a question where you can see what's going on without manipulating the window to some degree. And yeah, this isn't real helpful, as you can see. So what we need to do is zoom in a little bit. Now you can see there's some behavior going up here that might be good. There's nothing in quadrants 3 and 4, so we don't need y values even being negative. We don't need to be in quadrant 2. So we're going to zoom in here. I'm going to change my window and say, well, if we just go from 0 to 8, that's what we need to look at anyway. And I'm going to increase my y, or I'm going to decrease my y minimum, just make it 0. And I'm going to increase my maximum here to 40, just to play it safe here. Okay, and then let's graph and see what happens. So this will have us zoomed in quite a bit. Okay, there's the sinusoidal, and then that exponential coming through here. And again, this is only 8 units here, 0 to 8, so looks like we have a point of intersection around 6 or so. Alright, so we'll just use our calculator to find the point of intersection. And the first curve, second curve, and I'm just going to toggle over. You don't really have to do this, there's only one point of intersection, but it'll just take the one that's closest there. And so in the calculator here, we get 6.204 rounded. So I'm going to put 6.204. T is equal to 6.204. Okay? And again, you could have set it equal to 0 and found an x-intercept. You get the same answer either way. But there is our one critical number. So just to give you an idea here, here's what we just figured out. So from 0 to 8, there was one time where they were equal, giving us our critical number. And I'll put 6.204. And so again, back to the beginning, there's a lot of deviations from here that you can lose track of what you're doing. Back to the beginning, when is the maximum number of fish in the lake? Got it. I made my equation for maximum, which was a of t, the integral here. I took the derivative of it, and I set my derivative equal to 0 and undefined. I got my critical number, so right there. Now I have to test it. I don't know if that's a maximum or a minimum or what. So there's a chance it was a minimum. So maybe the maximum is at either 0 or 8. So let's see what's going to happen here. Now I could test these intervals for increasing and decreasing, but the question is just saying what is the greatest or the maximum. So to justify that, I actually just have to test my critical number and my two endpoints. So what we want to know is what was there at the beginning. Okay, we're going to analyze that, and we're going to compare that to what is happening at 6.204, and then we're going to look at what is happening at 8. Okay, I'm going to put 0, and then 6.204, and then 8 into the function that represents how many fish are in the lake at any one time. Well, that function is right down here. The one that we built, that we then took the derivative of. So I'm going to substitute those numbers into this equation here. So I'm going to write that again here. Remember, a of t is equal to this integral. Okay, so I'm going to put in 0. Now, I think you can see if I put in 0, my interval has no width here. That one's going to be 0. But now I'm going to replace t with 6.204. Then I'll replace that with 8. Now, for this question, because both of these can fit into one integral, I'm going to do it that way just to save myself a little bit of typing here. Just go to our calculator, and I'm going to put this in one integral. As you can see here, that's going to be fine. So I've already got this in here, integrating from 0 to 6.204, and I'm going to put in my trig function here, which was 20 plus 15 sine, and my numerator, I'm going to put parentheses around it, was pi t, close that, and then divide that by 6, and that is going to be the entire angle there. And then I'm going to subtract from that the other function, which is the rate they're leaving, and that was 4 plus 2, and 2 had an exponent on it of 0.1x squared. Okay, and we should be good there. And our variable of integration here is x. So let's see what the calculator gets us doing all that work. We get 135.015. 135.015. Okay. Okay, so then we're going to go back, save ourselves a little time. You just go up there and hit enter, and that'll allow us to come down here and edit this integral. And all we have to put into here is go up to here, and I'm going to make that an 8 instead. And let's see what happens at the end of the day. Looks like we get 80.9, rounded here, we get 80.920. Okay, so just to review what we just did there, so after we got our critical number, instead of testing for increasing and decreasing and all of that, we just tested the values. So at the beginning of the day, time frame, there was 0. At 6.2, it was 135, and at the end of the day, it was 80.9. So actually, it turned out this was the maximum. So this function must have been this derivative right here. If we were testing a prime was increasing, so that told us the amount of fish was increasing all day until here. And here was our maximum amount, and then it was decreasing till the end of the day. Okay, so it turns out maximum number of fish occurred. Let's give ourselves a little room here. So the maximum number of fish occur at time equals 6.204 with 135.015 fish between the time frame of 0 less than or equal to t less than or equal to 8. Okay. So there is our answer. So again, you had a function, you needed to find the maximum of it. If this was just like a chapter 3 question where you were given a function, find your maxes and mins, that kind of thing, you have your function, take your derivative, critical numbers, test them, all of that. This one was slightly different in that we didn't have to care about increasing, decreasing, so we don't typically test that. We just test the critical numbers and endpoints and get the value they're looking for. Okay? And again, falls into that category of this very important concept about building a function for a total amount. Initial plus increase minus decrease. Okay, let's wrap this up with part D. So part D on this question was missed by almost all students. Very small percentage got this right, and it's because there's a misleading part here that you want to be careful of. So it says, is the rate of increase in the number of fish in the lake increasing or decreasing at 5 a.m.? Well, here's what most students did. They read that question, they looked at the problem they just did and said, oh, well, 5 o'clock would be about right here, it's increasing. And by looking at the graph, they just said, oh, the rate's increasing, and they called it good. Well, that's, unfortunately, that's what can happen if the last thing you did was related but was different. So I'm going to go back to the question. I'm going to cover up part of this, and I want to see if you can recognize this. So what if I were to cover up the first part of the question here? And all I asked you was, what if this question wants you to figure out something about increasing and decreasing? If you are asked about increasing or decreasing, what should pop into your head? Increasing or decreasing means you're going to take a derivative and test it. take a derivative and test your intervals. Okay? Well, that's what many people thought you were doing right here, and you're like, yeah, it's exactly what I did, and at 5 o'clock it was increasing. Well, what's the problem? Well, here's the problem. The question says, is what increasing or decreasing? Now I'm going to remove the marker, and we're going to read what's under there. So whatever's under the marker, we're going to have to take the derivative of it and test it. Well, here's what's under the marker. Is the rate of change in the number of fish. Well, the rate of change in the number of fish is actually this equation right here. This is the rate of change of the number of fish. It's A prime. This is the thing that we have to take the derivative of. When you're looking right here, the thing that's increasing or decreasing is the number of fish in the lake. The number of fish in the lake is increasing and then maximizing, and the number of fish is decreasing. But that's not the rate of change in the number of fish. So actually, what was kind of sneaky about this one is you've got A prime of t is equal to E of t minus L of t. That's the rate of change of the number of fish. Is this thing increasing or decreasing? Well, then you have to take the derivative of it, which would be the second derivative here. So it'd be E prime of t minus L prime of t. And then you evaluate that at 5. So we can just put 5 in here, and let's see what they are. So in this one, we're going to take advantage of our calculator again, and we'll just see what these two numbers are. So on the number 8 here under the math button here, let's try that again. Number 8 here, okay? So d dx, and I'm going to put in the function and evaluate at 5. So once again, putting in this function here, 20 plus 15 sine, and we have pi x, close that, divided by 6. Okay, and that's our angle statement, and we want to evaluate that at 5. We get negative 6.802. So negative 6.802 minus, and let's put in the other function here. And once again, math menu, we'll go down to 8, d dx, and this was the L function, which was 4 plus 2 raised to the 0.1 t squared, and we'll evaluate that at 5, and we get 3.921. 3.921. Well, negative 6.8 minus 3.921, that's going to be a negative number. So let's multiply that by negative 1. We had that, and then we will add to it negative 6.801. 747. Close enough here. What do we get here? Negative 10.7. So it's about negative 10.723. And again, we don't really care what the number is. We just care about the sign. So it's about negative 10. Okay, so it's negative. Therefore, the rate is decreasing. Okay, so explain your reasoning. The rate of change, it's decreasing. It's decreasing because the second derivative of the amount at 5 is negative. That would be our explanation. Now, this letter D here, this is also, make sure, it was so easy to make this mistake. You always want to keep perspective of these questions, that you don't have to get everything. You get 2/3 of the questions. You get a 6 out of 9 on all your questions. That gets you in the 5 zone here. And so, as far as the point allocation, the first one was worth 2, the second was 2, and part C was worth 3. And there you are at 7 out of 9. So, don't let this one throw you. D was a little bit, it wasn't that difficult, but it was tricky because of the problem you had just done before it. So, the first one, basic, integrating a rate, get what the rate produced, average value, part B. And then C, very common with the two rates, build your function, take your derivative, test your critical numbers, and then C, a little bit of a wrinkle there, but not bad. So there was 2019 question number 1 on AP Calc AB. All right, thanks for watching. We'll see you next time.